Hey, John here. Let's look at the SD card driver code for the Z80 Retro board. The goal right now will be to get to the point where we can bring the card online by initializing it, read blocks of data out of the SD card, and copy them into the memory of the Retro board. In this case, we'll demonstrate how to read one block with an executable program in it that goes into a loop that you see running right here that counts in hex and prints hello from the SD card. The first thing you want to do is grab yourself a copy of the simplified specification for the SD card communication protocol. All right, click-through licenses don't reproduce in any means, so I'm not going to show it on my channel. I don't want to get a takedown request for the recording here. Okay, so this is where you get it. This one is what I'm talking about today is based on the version 8 of the document, and I refer to page numbers in here. These are like the PDF, I think, page numbers rather than the ones that are printed on there if you actually printed it in paper. Sorry, I had to pick one. This is more convenient for me, so I went this route here. Keep in mind, I mentioned before, all the cards run on 3.3 volts only. They're not 5. You'll fry the thing if you put it on 5 volts. So if you're going to play around on the bench and do other things, beware of that, okay? I'm going to be running my cards here. This driver assumes that we have a SPI driver. I already talked about that. There's other videos on my channel on how the SPI driver works that this thing is written to conform with. And it will run in mode 0. The tests I'm doing right here are all running on a house brand Micro Center card that you can buy with this URL here. And all these links are going to be in the description below this video, so you don't have to pause it and type all this junk in. Okay, so what are we doing here? Pages 242 to 264. It's not a bad read, and you'll be aware of what the heck is going on if you do that and glance through there. Even if you don't understand them, hopefully I'll fill in the gaps, okay? So what do we really need to do from the galactic view, right? Not even bird's eye, really high, from Mars. What do we want to do here? We want to send a bunch of clocks to the SD card. We need to send what's called a enter idle mode command, which is technically what they call command number 0. And it will also cause the card to enter into SPI mode of communications. And that's because the cards generally sport more than one kind of mode, and you really got to get the thing to wake up and to get into the right mode, or you're not going to be able to send any commands to it and data and stuff like that. After that happens, we're going to send a couple of other commands down there. Command 8, Command 41, and 58. And these things are going to put the card into... what happens is the card has multiple states, okay? And once it's in the idle state up here, you need to shift gears and get it into the what they call the ready state, which means you're ready to transfer data blocks in and out using these command number 17 and 24. Okay, so I'm going to go over these commands and the code on how we're going to exchange the data with the card. So if you want, you can implement more of them yourself. Like it might be cool to print out the the vendor information about the card. I didn't even get into things like asking the card what its capacity is and stuff like that. My only goal in this code here is the minimalist approach to getting the card online so that I can read a block and write a block. And this code will simply assume big possible problem there, right? But the code will simply assume that if these commands don't generate any errors, then the data on the card that we're going to be reading and writing will be valid and meaningful. All right. In other words, the retro board is not going to create partitions and things like that. That'll be done on the Raspberry Pi, in my case, or some other host system, and the Z80 Retro board will read and write blocks on the SD card when we're using it, but it's not going to be in charge of validating that the partitions are correct or anything like that. That's up to you to not screw that up before you put it into your retro board. Okay. If you really want to get into it, like I said, pull requests are always welcome if you want to dabble with this stuff. All right, so what does it mean to communicate with the SD card? All right, now remember we're using SPI Mode to talk to the SD card. What I'm about to tell you only applies to the card when it's running in SPI Mode. If you run it in SD mode or any other mode, the commands work differently, and the bits and stuff could be different. In many cases, they are. Okay, so SPI Mode, SD card interface. First of all, we're going to see that we're always operating in a half duplex mode. So you know the SPI bus interface is a clock and has a data out and a data in. So in theory, you can be sending data out and back at the same time, which is what we call full duplex. The SD card in SPI mode only operates in half duplex mode. So if time is working its way down the page here, what happens is the host, which is our retro board, can send a command to the SD card, and then later in time, it will send a reply back. Okay, so this is what we call like a ping pong protocol. Send something out, get a response back. Send another command out, get a response back. That's how we're going to see how the code is set up. All right, so what does a command really look like? All the commands that you'll ever send to the SD card, the commands are always 6 bytes long in SPI mode. They always have a command byte followed by 4 parameter bytes. Sometimes they're not used, but they're there. Followed by a CRC, cyclical redundancy check, which is 7 bits long, okay, followed by a binary 1, right? The command always starts with a 0 and a 1 bit over here. The command, all the commands are just numbered. So they're 0 to, as you have 6 bits, so therefore they're 0 to 63 are the command numbers. So all commands, 6 bytes long, start with a binary 0, 1, and they end with a 1 bit. Okay? Now, we're in half duplex mode there, and we're always sending bits, right, from the host to the SD card, no matter what. When we're using SPI, there's always something going out there, okay? And there's always bits coming back from the SD card. So how the heck can you call this half duplex? Well, what we do is whenever we're not sending a command, when we're the host, or the data, when we're sending a data block down to be saved into the SD card, right? So whenever we're not actively writing data from the host into the SD card, we will always send hexadecimal FF bytes. In fact, you can select the SD card and write a loop that forever sends down hex FFs here. Or when we're done, you could send a command, and then you can continue sending down hex FFs in here forever as well. That's fine. In fact, that's how you fill in, that's how you pad all the extra bytes in both directions, really. The SD card will do the same thing to the host. And this is because, as we will see, when a command goes out, we have to wait for a response to come back. We have to recognize when the response starts. So, and the SD card has to recognize when our command starts. So, if you enable the select line for the SD card, in fact, the specs requires you to send at least 1 byte of all ones down here, and we saw that in the SPI driver that I talked about before. You know, when the select line goes active, we send 1 byte out of all binary ones. So the SD card recognizes the first byte that is a 0, 1 in the most significant bits here is the beginning of the command. I can send as many as I want because it'll always be able to recognize when that happens. It'll also recognize that when I'm done sending the command, I'm not sending any more command data or anything else. All right, so these are the padding. These are the fill bytes when I'm not sending a command, or later on, as we'll see, when we're not sending a block of data down to be written into the card, okay? So what then does a reply look like from the SD card back to the retro board? Well, again, like I just said, it'll be padded with all hex FFs, right? There are always ones whenever if the SD card, I send it a command and I say, I want you to do something, or I want you to tell me about something. The SD card could take some period of time to do what you want before it sends this response message back. And there's basically three different ways to deal with this. Right now, I only care about two of them. Okay. So when the SD card is, I will say busy, but be careful with the use of that word, because that word means something else in different contexts when you're talking about the SD card. So when I say when it is waiting to finish doing what it's going to do to send a response, it's going to just fill up the master in SD card out line, right? The meso will have all binary ones on it. Eventually, it'll send its response, and we'll be able to recognize that, just like it recognized our command. This will start with like a binary 0. And so we can read and throw these away until we get a byte that has a most significant bit. I should do this like I did on the other one here. Then there's a status in here, right? So the most significant bit, when it becomes a binary 0, we know we're seeing this byte here. Now, some commands send out what they call an R1 response, and it's a single byte, and we're done. Other ones have some optional data associated with them. Those are R3 and R7 commands. I don't know why they call them these, because they always have 5 bytes in the response, right? Then there's other types of data, like if I say read a 512 byte block of data from the SD card, there could be the 512 bytes over here as well. All right. Now, that we'll talk about when we talk about transferring data. Right now, we want to get the card online so that we can start to transfer data. Okay. If you have a look-see at the SD card simplified specification and these pages, you'll see that to bring on the card, you're supposed to send out at least 74 clocks, and then command number 0, and an 8, and a 41, and a 58. So it should come as no surprise that you'll see subroutines in this file called send command 0, send command 8, and so on. It should also come as no surprise that you'll see a function in here that says read response number 1, read response number 7, and so on, okay? So hopefully these are somewhat self-intuitive, or self-defining names, right? And I try to put some doc in here that's actually meaningful and stuff like that. So let's start with sending command number 0 to the card, because that's the first thing we need to do after we power up a card. And as the spec says, this is the go idle command. Now, one of the reasons we do, first of all, if you power up the card, you must send a command 0 to get it into this idle state so you can start configuring the card, initializing the card, I should say, okay? If the card is already initialized, and maybe it's even been, like you press the reset button on the retro board, the card could be in the ready state already and wanting to transfer data blocks. So what you need to do in that case is also send it a command 0 to get it into the idle state so you can start the initialization process all over again. Because the retro board doesn't know what state it's in at all. It just simply does this no matter what. Therefore, the card goes into a known state, and it then just proceeds on. So what is this thing going to do? If you read the spec, it says the beginning of command 0, because the card select, right, the SSEL goes active, and then you start seeing command bits going out. It has this simple little logic that says if it sees what appears to be an SPI style command coming down the interface bus, the card will enter into an SPI mode. So part of the sending of command 0 will nudge the card so that it will operate in SPI mode. In contrast to SD mode or an SPI, or rather PCI Express and other protocols that some of the cards might support, okay? Then we also need to tell it what voltage it's running at. This is annoying. when you're running it at the default voltage, you still need to tell it, by the way, you're running at 3.3 volts, and you got to tell it like 3 times and ask then, are you okay with this? And the answer will be yes. And this is because in order to run it in a high-speed mode, you need to adjust the voltage levels and things like that in order to optimize the slew rates and the bit rates and stuff like that. We don't care. The Z80 can't get anywhere near taxing the SD card in any way. So we're going to just go through the motions and say you're running at 3.3, and it'll say okay, because that's the default, and all cards support that, okay? And when it's done, we'll be in our idle state. This thing will clobber every register, so be careful when you call it. And command 0 and all the various commands all look the same way when we look at the source code in the driver here. They're basically just 3 commands and a return, and I got a bunch of debugging in here. All right. Now I turn the debugging on in this build so that we can watch this go. And I found this incredibly useful when I was trying to figure out how to make all this work in the first place, because I had all kinds of bugs and oversights and things like that. So here's the deal. HL register is the address of the buffer, which you can see is right down here, okay? The B register contains the number of bytes I want to send, and I call this send command R1, which is a subroutine above this point in the file. We'll look at that in a minute. When it's done, in the case of an R1 command, the response comes back in the accumulator register because it's only a 1-byte response. If you're sending an R3 or an R7, we have to give it another buffer to hold the response data, because I can't just put 5-6 bytes in a register. Certainly not on a Z80. So the debug down here will say, here's the command that I sent. It'll print out the buffer for however many bytes there are in the buffer in hex, so we can see what's going on. Then it will, what it's going to do is going to print the R1 heading to let us know that this is an R1 command, and it'll print out the accumulator so we can see what the R1 value is that came back after the command 0. Okay? That's exactly what you want to know when you're debugging your code. When you're done, you're going to return down here. I play this game here where here's the bytes in the buffer. We'll talk about that in a minute. And then $ minus this label here represents the number of bytes that are in this buffer here, okay? So what's happening here, right? Remember, every command always starts with a 0 followed by a 1. And the most significant 2 bits. So what I'm going to do is, the way I wrote this code is, this number here is in decimal, which is what they use for all their command numbers, 0 and 8 and 55. Those are decimal numbers in the names of the commands. So the idea I had here was, this is going to be the command number, and you'll see that there'll be an 8 there if it's command 8. There's a 0 there if it's command 0. Then this thingy ORing in the 40 sets the second most significant bit, which has to be 1 all the time. Command 0 ignores all these parameter bytes, but all the commands are the same length, so they have to be there. And this down here is the hard-coded CRC value that I didn't want to calculate in my code. And we always set the least significant bit to a 1. All right, so we can clearly see that that's what's going on here. This message in its entirety is handed to you on a silver platter in the SD card specification under a little description where it says that if you're on a resource-limited system and you do not want to calculate the CRC value, because it could take a fair amount of time to do that, or use a lot of memory to do it, and you don't want to, if you're on a system that doesn't want to do that, what happens is it gives you the CRC that has to be there for command 0. Because remember, command 0, among other things, is what establishes the card to run in SPI mode. And command 0 has to have a legal CRC value, and it's not until after command 0, or maybe even command 8, if I don't remember which is which. It's not until after this command is processed that the card by default, when it's operating in SPI mode, will shut off the CRC requirements. Okay? So they just give you this to you, and they say, just put that in there if you're going to set all these bytes to zeros. That is what it should be. So we just hard code that in here and fire that baby off. When it's all done, and if it responds and it's happy, the CRCs will be disabled, and we don't have to worry about it anymore down the road. Okay. So what then does this really mean? It means that I have hard-coded the message with the leading most significant 0 bit, followed by the 1 bit, followed by the command number, and all that other fun stuff down here. And I send it out, and I read the response back, obviously, in this subroutine, because no one else is doing anything in here. So let's search for the command R1, which we saw earlier. It's at the top of the file. And I got a little bit of doc in here. It might be getting a little stale. What do? I send a command and read an R1 response message back, right? HL is the buffer address, B is the length, we just saw all that. Clobbers everything on the planet, and it'll return the R1 reply byte in A. And I put this in here for myself long ago. It's getting a little stale, but this is roughly what happens if you're going to send a command with an R1 response. There's the command byte. Well, first of all, we set the SSEL signal low, and we send out 8 clock bits, which we saw earlier in the SPI driver. And yes, I admit I probably shouldn't have put that in the SPI driver because that's SD card specific. I might have to refactor that code. But it's hiding in here is my point. So then we send the command byte, the 4 arg bytes, the CRC. Now, this is the wait for a reply. This is where we're going to see a loop in here that says, ignore all those bytes that are all FF. Wait until you get a byte that is the most significant byte equal to 0, at which point, arguably, you have already read the reply byte, and you select the SD card and go on your way and return the accumulator. So let's see what this code does. Surprise, we turn on the SSEL, we call write string, the SPI write string code, I talked about that before, and then we call read R1 to get the response byte. We set SSEL back to false, and we jostle around the registers here as noted, and we'll see this in a second. When this runs, it's just a coincidence, but I made it a documented feature that when this thing when this subroutine returns, both the accumulator and the E register will have the same value, which is the R1 response byte, which is handy because just about every subroutine will clobber the accumulator. This one does not clobber the E register, so I can put it back in the accumulator here and go on my merry way. Okay? So this is the whole transaction taking place here. Read R1 is where we're going to see this loop that discards the padding bytes, which is up here. Okay? So what does this one do? Read a response, read bytes until we find one with an MSB of 0, or bail out if we're reading for what appears to be forever. We never get it. We're going to bail out with a timeout. Okay. The last byte that we read, it will be returned in A, and I mean these words very literally. So if we bail out, in other words, the accumulator will have hexadecimal FF in it, which represents I have failed. Okay. And a copy in the E register as well. I note that it calls read 8, and see that if you want to know what's going on with clobbering registers and stuff like that. In addition to what's going on in here. So what is this going to do? It's going to load B with F0, which is 240 in decimal. I'm going to read 8 bits. I'm going to ask, is the most significant bit a 1 or a 0? If it is 0, we got what we want. We're done. We go down here. And again, this also returns it in A and E, and it's handy because we've already ruined the A, and we put it back in there, and we return, okay? If it is not a 0 in the most significant byte, we go back up to this loop, and we try. DJNZ, remember, decrement B. If B is non-zero, go to here. If B is 0, fall down here, and return with either all ones in the accumulator or a most significant bit of 0 followed by some sort of a status code. And you can read all about the status codes and what all the bits mean in the spec. All I care about is that it's either a go or a no-go kind of a situation here, right? So we're looking at command 0, which is going to call command R1 to send out this buffer of bytes, get the response byte back, we can dump it out and return, okay? Now, if we bring the window back in here, and I just reboot my retro board, we'll watch some debug statements come up, and you'll see the first thing that this test routine does is sends out the command 0, and you'll see the debugging code doing its job. just so we can get our bearings here before we start looking around at all the other code, all right? Now, if you hit Control A while you're using Minicom, it will effectively halt the display. So this thing booted up. What is it printing out? I'm running sdtest.asm. That's handy to know. So now we can know where the source code is for what's running. The Git revision is dirty, and I'll show you why in a minute. Short of it is, it's because I set the debug flag to dump all this out, which I normally don't do. So it's going to print out a message that says, hi, I'm going to read in the block number 0 from the SD card, which is normally where like the MBR might be. But in this scenario, there's no MBR. I'm going to waste the entire card on just putting a program on there starting at physical block number 0. And we'll see in a minute that that's what SDTest does. It reads in one single block into memory at address C000, and then it tries to execute code. Hopefully, something valid came off the SD card, okay? All right, so here's the command 0 in the debug that comes out. The first thing that comes out of here is because I said command 0, and it actually does a hex dump, as you'll see right here. Command 0, and I call hex dump over here. And therefore, this is the address where that buffer happens to be in memory down here, which is not significantly meaningful or anything. It just happens to be at address 3CF. And here's what the command 0 looks like. Hex 40, bunch of zeros, and a 95. And that is exactly what you would expect from 0 ORed with 40, a bunch of zeros, and 94 ORed with a 1. Okay, so we can clearly see that the right value went out. And the R1 response that came back is 1. And that actually is the everything is okay response. So this is exactly what you want to see. Let's boot it again just for fun, and I'll unplug the SD card so that it fails, and we can see what happens in that scenario. First, I'll wake the terminal back up, and press the reset button, and lo and behold, what does it do? I mean, think about this, right? There's no SD card. The schematic of the retro board has the master in line, right? Meso is pulled high. So if there's no physical card in there, it's always going to read in all ones. So what's going to happen is it's going to send out a command 0 because it doesn't know there's no card there. Well, what's missing from my driver? I never even read the SD card present. There's a little button, a sensor in there that I could actually ask, is there a card plugged in or not? I didn't even bother to check that. So what it does is it sends out command 0 to nothing, and it continuously reads bytes, and they're all going to be all ones. And the logic here is it's going to read, well, it was above the screen. It reads up 240 times it read before the B, the B register got to 0, and it bails out. So this message here says I can't read the SD card. It must have failed, and it doesn't work, and it's halting, okay? So let's look at the code that did this, the higher level, that called the command 0 here, right? And we already know it's in the tests directory, and it's called sdtest.asm because it actually prints that out when it boots up. Now, before we do this, let's do a git diff. So what I'm going to show you here is this is why the build was marked as dirty when it booted up here, right? So it says I'm in this specific version and it's dirty. Okay, dirty means I have changes that were never committed. This is the sum total of all the differences right now between the version that's in my GitHub repo and what I'm running right now. So what I did is I usually have the SD debug flag set to 0, and I changed it to 1. In this file here, which is the SD card driver library that we were just looking at. Okay, so in this directory, I have the sdtest.asm file that includes the usual I/O, port information, and a file called memory ASM where I define this load base. The idea is that's where the bootloader is going to read in the second stage boot code. And it just so happens that that is C000, okay? Now, this is code that runs out of the flash. We got to remember what's where here, right? So this is the flash boot code, and you can know that because you've seen this 100 times. And the flash code starts running at address 0, copies itself into the RAM, shuts off the flash, sets the stack pointer to a meaningful value. Now, this situation is different than the code that we've looked at before. This stack top equate that's above here, I'm going to set it not to 0 like I have before, right? Remember, I used to set stack top to 0, so when I push it, the items would go into like FFFF and then FFFE and so on, and start down from the top of memory. This is the first draft of the second stage bootloader, okay? And what it's going to do ultimately, when we're done with this, it's going to load in 16K off the SD card. Right now, it's going to read in just one single block. But the final version is going to read in 16K. And it's going to write it into the RAM, starting at address C000, all the way up through FFFF. So it would be very ill-advised to put your stack at FFFF and let it work down while you're clobbering it, reading into your SD card data, okay? So what I've done is I set it to C000, and because this stack is descending, it'll use the code below where we're going to load the second stage code into so that it stays out of our way. All right, so that's why this is going to load it at C000. I've also moved this standard default bit rate down to 9600. And so if you move J11A back and forth, you're either going to have 9600 or 115.2 if you set the bit rate on the SIO to come directly from the X2 oscillator, assuming you use the same frequencies I did in the schematic, okay? I did this because the VT320 terminal that I've been playing around with actually can't keep up at 19.2. It gets all kinds of little errors and stuff. So I just slowed her down a little bit. That's why I made this change. Okay, so we do the usual initialization of the CTC, the SIO, print out a hello message. We call test SD. And if this ever returns, we complain, which we just saw it do because it returned when it couldn't read anything. We'll see it returns if any of the commands fail. All right. And then we go into an infinite loop here. And we saw this before and how this all gets set from the make file. I don't know if I mentioned these dot labels here. I went through a couple of weeks ago when I was cleaning up the code, make it more presentable for YouTube. And it turns out this is probably a good idea. So I went and did it. Most assemblers provide a way for you to create localized labels, right? Think about this. I've got these include libraries, all the I/O and the memory. The whole reason I include these is so that code in these files can define labels and symbols and things that I can use in this file, like load-based, or GPIO, input port address numbers and things like that. So the labels that are defined in these include files, I want to use in this file. However, the labels that I use in this file, like stack top and debug, or even this like halt loop, things like this, I don't want them to be potentially conflicting or confusing code that comes from other files like the SD card library, the SPI, hex dump, SIO. What if one of these has a label in it that says, end or halt loop or something like that, right? We don't want them to conflict. So I tried to, go back and engage best practices, and that is to hide as much as I can from other files that don't need to see all this noise, these label noise, right? These are, a lot of them in assembly language are what I call nuisance labels. Things like this halt loop label here, it's used there and nowhere else at all, okay? Some assemblers even have a way to put labels in like this that don't even conflict with other parts of the file, all right? They're so local that they're only relevant here, okay? Now, this assembler is not that sophisticated. The way it works is if you start a label with a dot, the label can only be used in code that's in this current file. Even if you use an include, like I do at the end of this file down here, code in CTC1 ASM will not be aware of any labels in this file here with name like boot xc, okay, that this label will not be valid in there. And you can actually put a reference to, you try loading it into HL or something like that as a test case, and it'll say this label is not defined, even though you know for a fact it's in this file here. Remove the dot, try in the other test, and you'll find out, yes, it does work. Okay, so this has to do with hiding the labels from other files, all right? And this is, arguably good practice. All right, so that's why the ones in here are all starting with dots, because they're only useful in this file, and I don't want to have conflicts anywhere else. Like test SD, there might be one of those in the SD driver source code, either now or sometime in the future. You don't want to get conflicted. All right, so what's happening here? This is going to attempt to read one block off the SD card into memory at load base, and then jump to it. Okay, so what I do, here's where it says, hey, I'm reading block number 0. He calls SD boot, and I've talked about that before. All this is going to do is set 74 clocks by simply trying to read 10 bytes from the SD card. And as I said earlier, we always set Mosey to 1 whenever we're reading. Therefore, those 74 clocks will look to the SD card like a bunch of FF bytes. Okay, it also takes place without even selecting the card, by the way. And again, I've talked about all this before. So the card cannot in any way accidentally receive garbage commands or anything like that. That's what this does. Here's calling cassette command, SD command 0, which we just watched through. The details of that. And then we ask, did I get an 01 back? This code is really naive. I want perfect or nothing. If it's an 01, great. Move on to the next thing I want to do. If it's not a perfect response, immediately gripe and die. And that is exactly what happened right here. I pulled out the card. Can't read the SD card. This thing, the command status is not idle, blah, 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 blah. That came from right here. Okay? Return, go in an endless loop. All right. So what happens after command 0 is done? And where did I get all the ideas to do all this, right? Read the simplified spec. It literally says send a 0, then send the 8, and then do this, then do that. We simply do what it says, and that's that. Now, command 8, as we'll see in a minute, is not a R1 style command. It has a whole, it has an I don't know if it's an R3 or an R7 style response. It has a 5-byte response, is my point. Okay, so we have to tell it where to save the data. And we'll look at that in a second. Send out command 8, and when command 8 comes back, we inspect the buffer of data that comes back, okay? The first byte, as we will see in here, actually is the same as an R1 response for an R1 command like command 0 up here. And I'm going to just ignore all the rest of the stuff. So, naive driver. Did it say everything is fine? Regardless of the situation. And this bit in here, by the way, indicates that it is a 3.3 volt card or something along those lines. And it will be, because all cards are 3.3. The only options are whether you can have other voltages involved as well, okay? So I'm going to simply ask, does the first byte in this buffer, right, which is at the first byte in the buffer area, is it an 01, just like I did before? Nice inconsistency. I perhaps should have said ox 01 here and make them look the same. Whatever, I'll get over it. If so, I'm good. Otherwise, croak. Okay? Then what happens? I'm actually going to dump out some data here. Oh, if it fails, I'm going to dump out some data in return. If it succeeds, I go down here and I send out a command 58. Why do I send a 58? Because the spec sends to send a 58. What does this thing do? Yet more garbage about the 3.3 volts. And I don't expect to change it or do anything else. I'm just going through the motions here. Once again, I'm going to do this 58 command. And then what am I going to do here? I am going to then execute this command 41 in a loop. Let's talk about that in a second. What does this thing do? I read the OCR and I ignore the response. Actually, this is commented out completely, okay? The spec recommends that you can do this command 58 at this time if you want. And the only reason you'd want to do it is if you care about the voltages and stuff like that. And I don't care. I probably should delete this whole thing. I left it in as a comment for this exact point. And I forgot it's commented out. Just so that I would bring it up and tell you specifically, I'm ignoring this because I don't care about changing the operating voltage, okay? So what do? We send a 0, we send an 8. Then we're going to go into a loop. This loop, again, the spec says, send out a command 41, and we'll look at the 8 and the a command 41 in a second here, what happens in the lower level driver. But at the higher level view, what we're supposed to do is send this out repeatedly for, like, I think they say it could take up to 1 whole second or something like that. So it may very well be that this number needs to be bigger, but I set this to, in decimal, it's 128 times, okay? So what I'm going to do is I'm going to use B as a counter, and down here you'll see a DJNZ loop here, right? So here's my loop. Go up to this many times, and then I'm going to do this in a loop because the spec says so. What am I going to do? I'm going to save the counter variable, and then I'm going to reload it, as I count and so on. Some tricky stack work here to make that work right with all the branching and stuff. Keep the stack aligned correctly. So what am I going to do? I'm going to count up to this many times. When we're done, a command 41, when it succeeds, the response status in the accumulator will be a 0. So what happens here? If it is a 0, then a command is done, and we come out and go on our merry way. Otherwise, we wait a while. We go into a loop, and then we go back up to this loop here if we haven't depleted our total 128 times. If I don't put a delay loop in here, this would still work, but the whole thing would go super duper fast, and the number of retries would require me to retry a lot more than just this 128 here, which would require me to not use this instruction, and I would have to decrement a 2-byte value instead of a 1-byte value and all this other junk. So I just decided I would only retry a few times and then pause between each retry. Okay, you might have to play around with this stuff if you got a card that takes longer to initialize, right? So this is one of the things that got me into trouble early on. Couldn't figure out why my initialization wasn't working. So I made it take longer, okay? You could rewrite this and just use BC as a register pair to count up to 64,000 times instead of just 128. So anyway, what I do when this thing runs and completes, I actually print out, if the debugging is on, and it is right now, how many times I went through this loop. And it turns out it's like 2 to 5 times. So this has a little bit of elbow room in it, right? So again, I do this, and I do it in a loop because that's what the spec says to do. Now, I'm getting a little ahead here. Let's look at what's going on with the A command and all this other stuff. And the reason we need to look at it is because the A commands are not the same thing as the other ones. So what do? We went to command 8. Oops, CMD 8 in the doc. They're spelled in capital, so they're easy to search for like this, okay? What does it do? This is send interface condition and get an R7 style response. And what does it do? This is out of the manual. Make sure this is my interpretation. Make sure it's squawking 2.0 of the spec. If it's not, it might be an older style card, or maybe it's an a UC card or something like that. I'm not going to write the drivers for that. I have an HC card, and the code should also be compatible with an XC card. Everything will be right if you use those cards. What else we got? It should be confirmed that 3.3 works, and it must echo the AA back as the extra echo byte. If you read the spec, it talks about what these extra bytes are used for in the response message, which includes things like the all the different voltages that the card could support if you wanted to try playing around with it, which I don't, okay? Establishing that we are in version 2.0 of the spec also enables the basically you need to do this for our cause, right? I don't care about the voltage because I always support 3.3. The reality is this command also tells the SD card that the host, the retro board, wants to use version 2.0 of the protocol specification. Because if you don't do that, then this special bit in command 58 won't work right, and your A command loop won't work. It won't come online, and it won't become ready. This code won't work. Okay, so the one of the side effects of doing this command 8 is that it enables things that the card would otherwise by default not have enabled due to backwards compatibility. So what we're doing is saying, throw away your backward compatibility, your 15-year-old device that might want to treat it as a regular SD card instead of an HC card. Okay? Okay. What I should have said there is an SDSC card, standard capacity. So we're throwing away the old style standard capacity protocol and replacing it with the high capacity. That's what I should have said. Okay. Anyway, return the 5-byte response buffer in DE. And by the way, the response should look a lot like this. Okay. So if we're debugging, we need to save regs. We can bump it back out. Otherwise, we're going to do the same thing we just saw before. We got a buffer, we got a length. And this time we're going to say, hey, send me the 7-byte response. Here's the buffer. This is cut and pasted right out of the manual. A little bit of reformatting and embellishment by me. Apparently, we still want to have the correct CRC in this mode. Maybe this is the command that stops the CRC. Anyway, the point is after the, once you get to A command 41, the CRCs no longer matter. And that's all in the spec, all right? As well as these things. So these exact values are right out of the manual. And it says, if you don't want to do it, if you don't want to do your own CRC calcs, just send this, okay? And that's what I've done here for this many bytes. And let's see here, command 7. I don't think we saw that yet. If we send out an R3 or an R7 style command, turns out they both have the exact same format and they work in the exact same way. The reason they have different names is because the data in those 4 bytes, the 4-byte extra payload in the response, are used differently. But as far as the protocol goes and the code to get the bytes, it's exactly the same thing, all right? So I actually have R3 and R7 just do the same thing, okay? What do? Turn on the SSEL. We send out the bytes of the command. We then, look what I'm doing here. I do this a lot. Be careful. DE has the response buffer address in it. And when I call SD read R7, it wants the buffer address to be in the HL register. So by saving it before I call this, which clobbers all the registers, right? I can get the value back, but I'm getting it back into HL. So if you're new to Z80 and all this stuff, do not think I need to pop it back where it came from. So I push DE and then I pop it into HL. Okay, so this is copying the value that was in DE into HL, which is going to be the buffer address for the response. And I call the read R7. When I'm done with that, I go back to SSEL false. As we talked about before, there's the extra clocking down here with all the, the binary ones and stuff like that. You do all that simply because the spec says so. Okay. So here is the code for R7. Note the response message formats at SPI mode are different than they are in the SD mode. Okay. That's a note to myself, because when I first read the simplified 300-page specification, once in a while I'd look in the wrong darn section. And if you do look up, oh, what's an R7 look like? And you're just skimming through the manual and you read it, you're, whatever, doing text searches for R7 response, and you find the SD mode description of the R7 response, it won't look like this, okay? So make sure you're looking in the right section of the manual, which I believe is section number 7 for the SD command. Page 245 to 265 or whatever it is. Okay, so what does it mean to do an read R7? Well, the first thing you do is you read R1. Just like you do in all the other cases. Why? Because you want to throw away all those FF bytes waiting for the first byte that arrives that has the most significant bit set to a 0. Okay? Now, we just look at this code, and in theory, it might fail. And I don't bother checking down here. I don't care. This code is naive, but it's not truly problematic. Okay? Look at what's going to happen here. If this works correctly, let's assume it works right and go through it, and then we'll ask what happens when it fails. So if it works correctly, this will have returned, and the accumulator will have the byte in it. That is the R1 response. We're going to put that in our buffer right here. Buffer is pointed to by HL, store A into the memory at the address in HL, add 1 to HL, so that the next byte will go in the next memory location, and so on. We're going to populate that buffer. So once we get back from R1, the spec says we don't have to, wait for busy and all that other junk at this point. We can simply move on and read the next 8 bits for the second byte and the third byte and so on, okay, till we're done reading all the bytes, with which total of 5 bytes that are all in the buffer there, and then we return. Okay, so this doesn't have anything like, it doesn't return a value in the accumulator or anything like that indicate whether it's good or bad or right or wrong. All that's hiding inside the buffer here. Okay, now let's say read R1 fails. The accumulator will have all 1s in it, and it'll get written into our buffer here. We call read 8. Now, in theory, the SD card could send anything at all. But if it really is failed, it turns out the SD card will withdraw from the meso line, and the pull-up resistor will just set it to 1, and it'll read in FF, 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 most likely. Now, in theory, maybe the read R1 will fail because I didn't read enough, and maybe this will finally be the byte where the R1 response is finally valid, at which point we will have an FF in the first byte here, and the R1 will be in the wrong byte, and so on. Do I really care? Not really. Because if we look at the higher level code, when I say do the command 8 or anything else that's an R7 or an R3 response, I'm going to check this first byte to see, is this the right value that I'm expecting? That, either an 01 or a 00 in hex, depending on the context. And the answer will be, that will dictate whether I care about these other bytes. Okay? And if it turns out it doesn't work, so be it, right? All right, so that's what that's all about. Where is the, that was for command 8, right? So that's why this does and how it works the way it does. It doesn't really have a response byte in the accumulator. It has the buffer in, the response is in the buffer, okay? All right. Now, after the command 8, notice that the next thing we do is a command 41. Now, if you think about it, remember the command, the message, the commands have 6-bit values for the command number. So that might have been a little short-sighted, because once they got up to command number 63, they ran out of values. So what happens is they decided to invent A commands, which are these, what they call an application command, all right? What an A command is just same as any other command, except you first send command 55, then you send the A command down there. So this is kind of like an escape. It says, oh, by the way, this is the extra set of commands. So obviously they went from 0 to 63, and when they wanted to have command number 64 through 127, they needed a way to do this. So the way they do it is send out a command 55, which doesn't do anything at all other than simply be command 55, which tells the SD card to treat the next command, which is sent like any other command, as an A command instead of a regular command. And it's nice and confusing because there actually is a command 41 in addition to the A command 41. So you need to remember which one you're dealing with. Fortunately for us, we don't use command 41 at all, so it should keep it to a minimum. So what does it mean to then send a command 41? It means to send command 55 followed by command 41. Now you'll notice I completely ignore the response from command 55, which is implemented right up here. And this is an R1 response type of command. Little doc says, oh, you send this before you send in the so-called A command messages, okay? And it works the same way. It's got your little buffer down here. It's command 55, no arguments. Don't care about CRCs anymore after command 0 and command 8 are done, okay? And I'm going to ignore the response at my great peril, okay? So I've done what I'm supposed to do. It would probably be a good idea, honestly, to check the response in here and bail out if it doesn't work. Because if it doesn't work, it might very well be that this could be misinterpreted as command 41. If this succeeds and this fails, right? So this is not the safest thing to do, but I'm going to get over it. Again, pull request welcome. This can be robustified if you want, all right? So this is going to do the same sort of a thing as you've seen before. Send out a regular command with a buffer and a length, and it's an R1 command. We've seen all that. The buffer down here is a little more, we finally got some parameters in here. I did some Googling around on the internet. It's totally not rock solid clear to me what we're really supposed to do here. And so this is a little bit dubious. It turns out on page 263 in figure 7, number 7.1, version 8.0 of the simplified specification, footnote number 1. It says that we want to set the HCS bit here if we want to verify, or if we want to, talk to an HC or an XC card. Okay. Notes are on the internet also about setting the supply voltage information in this, but they don't say to do it in SPI mode. I don't really know. So what I've done is I set the HCS bit because the spec says so, which is the bit hiding in that byte right there. And I ignore what the internet says here. And by the way, this works on my Micro Center card. All right, so if you know more than this about me, which would not be hard to do, by the way, this is my first time I ever used an SD card. Let me know. In other words, there might be a need to send another flag or something in here. In any event, this definitely works. And you can see this is command 41 becomes a command 41 because I sent the command 55 first, right? So there's the 41 and the magic bit. This one has some parameters finally. No CRC, least significant bits always set to a 1, just like anything else. And when this thing is done, it's going to respond. What do we got? This is an R1 style response. So when we get done with the A command, we can check our accumulator down here. You can see I save it when I'm dumping out my debug output. Okay. So the accumulator goes back to the higher level code as the response byte. Okay. Now, earlier I did say that this is handled a little bit differently. I probably misspoke a little bit there. Let's look at this a minute. Too much going on in the old brain. Why did I send a destination response for an A command? I do not know. I mean, there's been different versions of this driver, and I'm going to claim, there might be some vestigial code in here. What is this thing doing? A command, send a return, return. I may have had a version of this earlier where I did use a response buffer. Okay. This clearly is not using it at all right now for either command 55 nor the command 41, because this doesn't use it either. They both are R1 style messages. So it turns out we have a benign bug right here. Okay, because it doesn't care. Now, the A command 41, if you look in the spec, this one, I'm not going to check to see if it's set to a 1. All right? The difference between the commands that come before the A command 41 and this command is that the least significant bit in register 1, in the R1 response, indicates that it is in the idle state. What command 41 or more, what A command 41 does when it finally finishes is it takes it out of the idle state and it moves it into the ready state. Therefore, the correct R1 response for this command is 0 and not a 1. That's why this is different than the ones we saw before. All right? This is probably should be deleted. My bad. And then I said earlier, we wait a little while and we do it over and over again. And we do it over and over again because the SD card spec says to do it over and over again. Okay? When it is done, we assume all went well. We're going to print out, by the way, here's how many times I did it for debugging purposes. Now we move on to command 58, which is the command that we can finally, after a command is done, a command 41. Once this is completed, the spec says do this, and then check the response. And there's a bit in the response that we'll see down here. In fact, it's this one right here. This is the logic looking at the respond value from a command 58. This thing, if this bit is set to a 1 in our buffer, and this one is a a multi-byte response, so we reach into the second byte of the response of the command 58, and we ask, is that bit right there set to a 1? And if it is, then we know we can use version 2 of the SD spec, and the card is either HC or it is XC. And the reason we need to do that is because the code that I wrote to implement the reading and writing routines to move the blocks of data back and forth only works if it's in version 2 of the spec in HCXC mode, okay? So this one, we really do want to check this. I can see a potential for a problem in here because I didn't bother to check the first byte of the response, right? So there's a bug in my code here. I probably should load A with load base to look at the first byte of the response to command 58. Due to the reasons I said earlier, to make sure that the first byte says that the 58 completed okay before I move on to read all and look at all the other bytes, right? Because let's say 58 didn't work and I'm getting all binary ones back from the card and it times out. Well, that bit there will be set in that scenario, will it not? All right. So this is a command that it could fail, and I wouldn't necessarily know about it due to the way I wrote this code. It could be done better. Yes, I admit. But this, for now, is good enough to get our, our first draft working, getting the card online. All right. So again, somebody once posted something to my channel saying, "Oh, you don't leave anybody anything else to do." Well, here's some stuff to do. And actually, I think this, and I don't laugh just saying, "Ha ha ha," no one's going to do this. But this probably should be done, and we should validate all these things and generate better error messages. And it would be nice if somebody happened to have an XC card and see if all this works. Okay, so let's look at the 58 in here. Command 58. Which is right here. What does this thing do? It's going to go out and get an R3 response. It's used to ask the card what voltages it supports and if it is the right kind of card. Okay, so what do? I send out the buffer. I read an R3 response into the buffer that's pointed to by the DE register, and this is the same as the R7 code we just looked at a second ago, and I dump out what I did and what the response buffer looks like, and return to the caller. Okay, and there's the 58 and the usual stuff in here. No CRC, set the least significant bit. All right, so that's pretty straightforward, and yes, I probably should have validated the first byte in the response buffer. My bad, I'm guilty of being lazy and a slob there. Okay, so let's see here. 58, when that's done, we then move on to the real deal. Right here. So once we're down here, once 58 is done, actually once 41 is done, we know we can start transferring blocks in and out of the card. When 58 is done, we know how to transfer blocks in and out of the card. Okay? Now, I look up at the clock on the wall, and I can see that this video is, again, getting into overtime. So this is probably a good time to take a pause, because at this point, we're fully online with the SD card, and we can move blocks in and out, right? The first thing we want to do is be able to read from the SD card. And this is the logic right here. If you want to work ahead, you can unravel all this with the spec. And one of the reasons this is probably a good place to stop is that Command 17, and if you think about it, this isn't just send out a 6-byte command and get a response back. Well, the way this is going to work, spoiler alert, if we look at a command 17, and we'll get into it next time, the short of it is, it's going to send out a command, and then it'll include like the block number. Hi, I want to read block number such and so, and then the SD card will come back and say, okay, I'll do that. Then there will be the block of data that comes back from the SD card. That's not too bad. It's just got like this double response, okay? And it's going to have 2 times when the card is busy and waiting, right? So it'll when you read the response for the command 17 itself, it might wait when it's reading like an R1 or an R3 type response. Then it'll be busy when it's getting the data from the flash memory, and it'll be busy again, and then there'll be a block that comes back, right? So this is more going on. And when you're writing, you'll find out it's even worse, because there will be a command, and then there's an acknowledgement of the command, and then the host has to send the data the other way, and then the card could be busy waiting to do the write operation, and so on. All right, so these will take a little bit more code than the simple, get online, become, verify the operating voltages and stuff like that we talked about today. All right, so we're almost there. The very next thing is read and write blocks. So tune in next time, and we will go over the details of moving around these data blocks. Thanks for watching. I'll see you next time.